And hi, hello everyone. So last time at Billboard meeting, I have presented my work on the structure control of floating wind turbines. And since then, my research has moved to the wind farm level. So today in this presentation, I will give an overview of this part of work. So first, I will talk about the background of this research, and then the main work are divided into two parts. So the first part is about the uncertainty quantification of wind farm weak models, and the second part is about the machine learning-based wind farm weak modeling. And also, I give a brief result we recently got in the area of machine learning-based control of wind farms. And finally, I draw the conclusions and also talk about the future works. So here, this is a photo of the Hornstripe wind farm in Denmark. As we can see from this photo, the downstream wind turbines operates in the wake generated by the front turbines. So as we can see here, the wake's impact of the front turbine to the downstream turbines is called wake interactions. The wake interactions can greatly decrease the power generation of the turbine and increase their structural load. So in order to mitigate the wake interaction effect, during the design phase, the wind farm are optimized in order to have an optimal layout. And during the operation phase, various control strategies are designed in order to steer the wake generated by the front turbine away from the downstream turbines. Here we show an example of a simulation case of 6 turbine wind farm, and we used the yaw control strategy. As we can see here in the for the front turbine, it operates in the yaw condition such that the wake it generated is shifted away from the downstream turbines, so that the overall wind farm power generation is optimized. But in order to achieve the optimal control of wind farms, efficient and accurate wind farm wake models are urgently required. In the current literature, the wake models fall into the following category: numerical models and analytical wake models. The numerical models, they are usually of high fidelity, and most of them can simulate unsteady wake details, but they are very slow to run. For example, a large eddy simulation usually takes several days on supercomputers with several hundred CPU units. Here on the bottom left, we show an instantaneous flow field of a large eddy simulation carried out by the software SOFA. So we can see the flow details are all captured. On the other hand, the analytical wake models, they are usually of low fidelity. Most of them can only simulate the steadied wakes, but they are fast to run. So this makes them very suitable for doing layout optimization. And here on the bottom right, we show typical results of the analytical wake model simulation. As we can see, it can predict the overall trend of the wake, but all the flow details are missing. So in this work, for the part one, by using high fidelity CFD data, we investigate the uncertainty quantification of analytical wake models to further improve its reliability. And in the second part, we developed a machine learning model to develop a new wake models that can capture unsteady wake details while running as fast as the analytical static wake models. So this is the first part. So in this work, we focused on the analytical wake model Fluoresce. The Fluoresce model consists of mainly 3 parts: the wake deflection, wake expansion, and the wake velocity. So the wake deflection models the weak centerline by taking account of the rotational effects and the yaw effects. So after determining the weak centerline, the weak expansion model divided the weak zone into 3 subzones, as shown here in this figure, the near weak zone, the mixing zone, and the far weak zone. And the weak velocity model gave the velocity profiles within each subzone separately. And we summarize all the empirical model parameters in Fluoresce model here at the bottom. As we can see here, in total, there are 12 model parameters. So the traditional approach, in order to use the Fluoresce model, we at first generate a set of high fidelity CFD data, then we calibrate it to find an optimal set of model parameters in order to minimize the mismatch between the model predictions and the CFD data. But in this case, how accurate the prediction results are is unknown. So in order to make model predictions with quantified uncertainty, for the first time, we introduced the Bayesian UQ approach in weak modeling. So we model the parameter Z as random variable, so it can be characterized by its probability density function Pz, and we use the Bayesian calibration method to obtain the posterior distribution of the probability density function Pz. So once the posterior distribution of the model parameters is obtained, we can move on to prediction. So the prediction aims at obtaining the posterior distribution of the quantity of our interest, the QOI, here denoted as Q tilde. In order to do so, we need to propagate the posterior distribution of parameter Z through the computer model, here the analytical weak model. Then we can get the statistics of the model predictions. And from the posterior distribution of the QOIs, we can calculate its mean value, the standard deviation, and confidence level, and so on. In order to get the posterior distribution of the model parameter Z, we still need to specify the prior distribution Pz and the likelihood function. So here we choose a uniform distribution for the prior, and we determine the prior range by trial and error. And the likelihood function needs the construction of a stochastic model. Here we give the details here, but we mentioned the main idea is to model the model inadequacy term here as an multiplicative Gaussian eta, and the measurement error is modeled as a Gaussian here denoted as E, so that we can explicitly express the likelihood function. So after this, we can employ a sampling method to get the posterior distribution of the model parameter Z. So here this is the calibration results for all the 12 model parameters. So as we can see, all the model parameters are clearly identified. So with this posterior distribution of the model parameter, we can propagate them through the model to get the prediction results of our interest. As we know, in the wind farm cases, we are mainly interested in the prediction of the power generation. So here we considered a case to validate our results. This is a 2-turbine prediction with downstream spacing of 5 rotor diameters. And we also run large eddy simulations by SOFA for 500 seconds as the baseline, as the reference case. For all the test cases, in total, we carried out 30 test cases. We gave the SOFA results, the original Fluoresce predictions, and also the Fluoresce with quantified uncertainty Here we refer to it as stochastic Fluoresce. So this is for the front turbine's power generation. We can see the Fluoresce and the stochastic Fluoresce give exact the same results, which is reasonable, as we can see here at the bottom. The front turbine are operating in free stream, so the week's prediction do not have impact on the power generation of this turbine. So we are mainly interested in the real turbine's power generation. Here we can see on the first figure is the average power, the bottom figure is the power fluctuation. We can see the Fluoresce with quantified uncertainty match with the SOFA results much better than the original Fluoresce. And also we have especially for the power fluctuation predictions. So with this stochastic Fluoresce we developed, we can use it to do optimal wind farm control with also consideration of power fluctuations instead of only optimizing the power generation mean value. Then we'll move to the second part, is the machine learning based wind farm week modeling. So in this, this is the main flow chart of this part of work. So the main idea is at first we generate a set of large eddy simulation data with turbines operating in different conditions with different yaw angles and different inflow velocities. And from these unsteady weak scenarios, we build a machine learning model to learn from this database. And after training, we obtain a data-based machine learning model, which can be used for fast wind farm simulations. And this data-based simulator we developed can simulate the unsteady weak behaviors of a wind farm like this one within several seconds on a standard PC. But with traditional method, with large eddy simulation, it would take several days on a supercomputer using several hundred CPU cores. And here we carried out 2 test cases to demonstrate the performance of the developed weak models. The first one is the simulation of a single week for 300 seconds. The first the yaw angle begin from the -20 degree to eventually 20 degree. As we can see, from the left figure, the weeks it generated is deflected upwards, and at the end of the simulation, it is deflected downwards. So this is all reasonable corresponding to the relevant yaw angles. And to fully demonstrate its ability to simulate large wind farms, here we give the results of the simulation of 3 × 3 wind turbine array for a simulation time of 300 seconds. And later we will show a video of these simulations. We can see that our model can actually capture the unsteady weak behaviors similarly as large eddy simulations, but we just take several seconds on